Means suppose this frame is rotating. This frame is rotating. Then one has to construct kinetic energy and Lagrangian for the system. Suppose this frame is rotating around this axis, an angular velocity omega. And this is it. So for a, let us start with simple pendulum. Point causing inertial mass L, x-axis, y-axis, z-axis. The particle is moving on the plane, straight plane. So therefore, this is a constraint, polarity constraint. So x square plus y square minus L square is equal to 0. Z is equal to z minus some constant is equal to polarity constraint. Number of constraints are 2 and the number of mass point is 1. Degrees of freedom. So the general formula is dn minus k. So since it is 3 dimensional, therefore 3n minus k. So 3 into and 1 minus 2, that is equal to 1 degrees of freedom. Now what is the transformation? So the next thing is we have to compute the position vector. Position vector. R vector is equal to xi plus yj plus zk. To get x, y, z, this is not the proper coordinate product because there are these coordinates x and y are not linearly independent coordinates. So we want to work in a coordinate that are linearly independent and that are free from constraint. So during dynamics, that should not violate the constraint. We call such a coordinate as generalized coordinate. So theta is the generalized coordinate. Which is dimensionless here. And for that, from Cartesian to generalized coordinate, we should write a transformation equation. X is equal to L. So this is x, theta is this one, L sin theta, y is equal to L cos theta. Therefore, R is L sin theta I plus L cos theta, and this is negative j axis. Therefore, I call it as minus j plus some constant times k. This is the position vector. So the velocity is L theta dot cos theta I minus L theta dot, then this is plus L theta dot sin theta j and some 0 times k. So this is the velocity. Therefore, kinetic energy is so therefore kinetic energy is half m L square theta dot square cos square theta L square theta dot square sin square theta plus 0. Therefore, simply L square theta dot square. And the potential energy is there is at the equilibrium. This is V is mg dash. Suppose I choose the zero of the potential at this point, then this is mgh at the equilibrium minus mg, I call it L, mgl cos theta. So therefore mg L 1 minus cos theta. When I put theta is equal to 0, we are taking this at this point potential energy is 0. Otherwise, if I choose a 0 of the potential at this point, then I should write minus mg. This is for this case. Suppose I want to extend this to this rotation field. Up to this, there is no change. The same thing we have to come. Due to this rotation, the frame is rotating. Shall I write this? So since the frame is rotating by an angular velocity omega, let me call omega j cap. Then I have to use this formula to compute the velocity. This is body center of axis, that is the frame in the rotation frame, and this is space center of axis, that is inertial frame, and this is the omega in which the angular velocity in which this frame is rotating, and this is the position vector. So I am going to substitute to get the kinetic energy. So V small p, that is equal to dr by dt. Dr by dt is this one. So L theta dot cos theta I plus L theta dot sin theta j plus 0k, that is 0k is 0, plus omega j cross r vector. R vector is this one. L sin theta I cap minus L cos theta j cap plus some constant times k cap.
So we told that dr by dt is in the inertial. dr by dt is
This part is
left hand side is the inertial frame.
This is in the inertial
frame.
and this is this is body center of axis.
Yeah, but that formula was derived only for the inertial frame, not the
No, this I am extending this system to the rotational frame. So the same arc.
First term, the dr by dt, first term you are writing is derived from the rotational, from the inertial frame. So can we transfer it directly?
You will have to compute like that.
That dr by dt has itself has been applied only in
Within the frame.
We are within the
oh, it's in the frame.
Yeah. Within the frame.
Inertial frame. Because suppose you see the rotation frame.
You obtain here, to get the inertial velocity, you have to use the other term also.
So you consider the rotating frame of
Rotating.
It's not inertial.
It's not inertial. So get the velocity with respect to the inertial frame. So dr by dt is not an inertial. dr by dt plus omega plus r is inertial.
So therefore, if I multiply j cross j here, j cross I is minus k, and this is 0, and this is I. So this is L theta dot cos theta I plus L theta dot sin theta j, and this is minus omega L sin theta k cap plus some constant omega c and I. So that constant is added here, L theta dot cos theta plus omega c I plus L theta dot sin theta j cap minus omega L sin theta j cap. This is the velocity. This is this velocity. If I take the dot product with the same velocity, then I will get the kinetic, then I can compute the kinetic energy. To get the potential energy, I substitute this. Say potential energy is not going to affect because the rotation is about. That is, potential energy is not going to affect. This is due to only gravity. So V is same. V is the same. That is my MGL 1 minus cos V. Okay. Yes. So this is what. Now we have to construct Lagrangian for the rigid body in the inertial. Let us take here. Draw like this. a rod, then this L, this is axis, origin, z axis you can take in this direction. So let us choose the center of mass point to be this point. So this is xcm, ycm, zcm. So this is center of mass point. Therefore, R vector is, R center of mass is x center of mass plus y center of mass plus z center of mass. Okay. So you can write in terms of angular coordinate also, but I am not writing, just I am writing in terms of center of mass coordinate x, y, z. Then R dot cm dot R dot cm you can compute, that is xcm square plus ycm square. Suppose if it is motion on the plane, then z is not going to contribute. Correct? So suppose z is constant, so therefore this is 0. Now the kinetic energy of this system is the kinetic energy of the center of mass plus the kinetic energy about the center, that is about the center of mass. The kinetic energy of the center of mass is half capital M, that is the total mass of the system, and times xcm square plus ycm square. So a dot, sorry, there is a dot here, kinetic energy. Next is about center of mass, rotation. So this rod is rotating with an angular velocity, suppose some velocity, this rod is rotating like this.
Minor question. I'm wondering how the rod rotating.
This,
Is it like this? Oscillating.
oscillating. Then this is,
Then x dot y dot should be 0. Center of mass at rest.
no, this is oscillating like this.
See, I understand you are going to do it on a plane, right?
Yeah. Oh, right.
Oscillates on the plane.
So therefore this oscillation.
That is the angular figure. I think better is first to find out degrees of freedom and then write down this.
So x dot is 0. X dot cm is 0. So it's oscillating. Center of mass at rest.
No, but see, the way we can, the rod can actually,
So rod can go like this.
So the degrees of freedom is,
see, the point is, there is always some danger in drawing the diagram, because most of the times we tend to associate drawn diagram to find the degrees of freedom. Usually it will take some time for us to get established the notion that you must use all types of initial conditions should be accommodated for a given set of degrees of freedom that you want. So when you draw like this, you better draw a slanting like this and then a rod, so that the angles should be obvious.
okay. So suppose this pendulum is like this. The rigid rod is going like this. Then the motion of the center of mass x, y, and this I can relate to the center of mass. Therefore, 1 degree of freedom, and this is above the center of mass. This motion will be there. Therefore, this system has 2 degrees of freedom. 2 degrees of freedom. So this motion above the center of mass, I call it by half I alpha.
So you got
Alpha dot. So this is the kinetic energy. Then total kinetic energy is half m. If I express in terms of some theta angle, then this is,
So you need two angles, so
Theta.
one is that. You have 2 degrees of freedom, right? So there's one theta, then there's another 5 some other angle.
so this I can write this by transforming the coordinate, but we can do that. So simply I am writing like this, plus half I alpha dot square, and V is equal to this part. That is, due potential energy due to this gravity, therefore m g G.
Omega what I wanted alpha or omega only. Alpha is rotation speed about the center of mass. But then alpha?
Alpha is omega.
Which angle is alpha? Oh, there you mark that.
No, not this. You can write. See, actually, this angular displacement one can from the center of mass I can translate. So that is why this term. See, the center of mass point.
The road is free to rotate, no?
Yeah, that is
alpha angle.
Yeah, that is alpha. And this oscillation, I can either theta, but that is, I didn't transform to theta, I just put x, y, because of this. And the potential energy is not going to change. Potential energy is YCM. That's all. This is minus YCM. Nothing is going to change. Now this is going to rotate.
It's also
Rotating. If this frame is rotating, what will happen? This frame is rotating by velocity, angular velocity, omega is equal to omega times j. Then, this is not going to change. This part, PR is not going to change. This is not affected. Therefore, you will get XCM I plus YCM J plus ZCM. Okay, this is some constant times K. There is RCM. This you translate like this. So V, this is equal to the RCM by dt plus omega cross RC. Compute this and substitute to get that. Is that correct? This you can write in terms of theta, that you can transform. Otherwise, you can directly compute.
Maybe you can give pass and